All right, so this is continuing the example from the previous video. We've got the Invised-Burgers equation. We've got two different initial conditions. Right, and I've changed my notation very slightly. We know that we're on characteristics where x is a function of t, and at the initial condition t is 0, so we can write this as a function of x naught, if you like. So our characteristics are these straight lines, rho at x naught times t plus x naught. Our next task is to sketch these characteristics. So I'm going to do that sketch on the axis over here. Firstly, we've got to plug in values of our density. That's not much use trying to guess what this is when we've got it right here. So we've actually got to stick in some numbers. So let's do it for case 1. 0. That means this is 0 if x is less than or equal to 0. So we're left with x naught when x is less than or equal to 0. Right, this is 1, so that means we get 1t, so t plus x naught if x is bigger than 0. Okay. Note that we typically draw our characteristics where x is the abscissa and t is the ordinate. This gives x as a function of t, which is not what we want. We want t as a function of x. So let's go ahead and rearrange. Obviously, there is no way we can rearrange the first one, right? X is always constant. That's kind of easy enough to draw. X equals a constant in time is just a vertical line. Right? And these are different possible values of our starting point. So that's the characteristics in that region. We do, however, still have to rearrange this, although it's a simple rearrangement. Okay. So if t is 0 at our value of x naught. So that's nice. It has slope 1, right? So I'm trying to draw these lines at roughly a 45-degree angle, and assuming that the axes are equally scaled. But we kind of do the best we can. So these are lines of slope 1, t equals x minus x naught. And these are different values of x naught. There's obviously two critical characteristics here, the ones that divide the domain up. We've got one there, I've got one there, right? That's the one just to the right and just to the left of the origin. Really, we can write in what these lines are. This line is t equals x, and this is, x equals 0, right? We know what's happening to the density on the right of this characteristic, right? Our solutions, our density is constant on the characteristics. We already established that. So everything to the right, like this, we know that the density is 1. Similarly, everything to the left of this characteristic, we know the density is 0. So we want to write this mathematically. So case 1, rho equals, this one's easy, x has got to be less than 0. X less than 0, or less than or equal to 0 in the way that we've set it up, the density is 0, right? We know what's going on in that region. Everything to the left of this line, right? That line is t equals x. If x is greater than t, we're in this region here, right? These are just different points where x is greater than t. So for x greater than t, density is 1. We have no information in here. This region here, we have nothing. We don't know what's going on. We have to rescue our problem by inserting fan-like characteristics, right? This is a fan-like object, I guess, where the characteristics change gradient. We can work out the region, however, where we have no information. That is, this region in here. It's pretty easy to state that mathematically. X is greater than 0, less than or equal to t. Right? And we don't know what's going on in there yet. That's just where we're going to leave this. And we're going to move on to the next example, which also has a fan or a region like this, but it's a bit different. The gradients are different, so it's worth seeing. I'm going to work that one out a bit faster, however. Right, we've seen how to do this one slowly, so we'll just do case 2 over here. When we integrate, or when we take this and multiply it by t, we're going to get 2t plus x naught, x less than or equals 0, 3t plus x naught is greater than 0. Rewriting that, so we got these equations. That tells us that in this case, these slopes, the slope of these characteristics, the top ones here, that's 1/2. Slope of these characteristics, 1/3. So that is these characteristics that originate x less than or equal to 0, that those characteristics are steeper than the characteristics which originate for x greater than 0. So let's just sketch this in, and we're not going to try and get these gradients perfect. We're just going to try and represent what's going on. So these are the steep characteristics, slope of 1/2. Right, I'm just drawing it a bit shorter, so I've got some white space to write in. These are the steeper characteristics. Slope of, sorry, these are the less steep characteristics. Slope of 1/3. So the black one here is t equals x on 3, because x naught is 0. And we've got this line here. Oops, I'm sorry. That's x naught on 2, right? Because it's just to the, we pretend that it's just to the left of the origin. Just to the right of the origin, we got x on 3, right? So within the shaded region, we again have no information. It's like the thing in the other case. But we can work out what's going on to the left of this curve, the left of the exon 2 characteristic, and to the right of the exon 3 characteristic. On this side, rho equals 3. If x is greater than 0, right, which is basically everything to the left of this to the right of this characteristic, as time evolves, like so, we're going to see rho equals 3 because the density rho is constant on our characteristics. Everything to the right of this characteristic, rho equals 2. So we can start building up our solution again, except we won't get any information in this gap. We still don't quite know what to do with that. So rho equals 2 if we are less than this line. That means x less than 2t. For some reason, we always cast these up in terms of x rather than in terms of time. I guess the spatial coordinate is more sort of interesting to think about than the time coordinate. You know, you just think of time rolling on and changes in space. It's sort of more intuitive. So you rewrite this as x as a function of t, which is 2t, obviously. And if you're below that threshold, right, which is there, x less than 2t, you're going to have rho 2. It's less than or equals 2 by the way that this is set up. Similarly, if we're bigger than this threshold, we've got rho equals 3. There's the gap, obviously, between 2t and 3t. We currently have no information there. And again, we're going to have to insert fan-like characteristics into this problem to get an answer.